In this video, we are going to talk about the product and the quotient rules that can be used for taking the derivative of functions that have two items that are multiplied together or two items that are divided. This first slide shows us what the product rule is. We're starting with two different functions, f of x and g of x, and both of them have to be differentiable. We can take the derivative on some particular set of some interval of x values. If we want to take the derivative of those two functions multiplied together, we have this formula that we use. We take the derivative of the first function, that's this part, and we multiply it by the second function. And then we add that to the derivative of the second function multiplied by the first function. So what we're doing is we're sort of, in a way, if you think about it, taking the derivative here and multiplying it by this g that's left. And then we're taking the derivative of this and multiplying it by this that's left. So the way that we'll use this, let me do an example problem. Suppose that we have a function, we'll call it capital F of x, and it is 6x to the third power multiplied by 7y to the fourth. Let's call this first function f of x, and then we'll call the second one g of x. The derivative of f of x is 18x squared, using the power rule that we talked about in class. And then the derivative of g of x is 28y cubed, also using the product rule, or sorry, the power rule. So when I want to find the derivative of the product of those two functions, I'm going to take the derivative of the first function and multiply it by the second function. And then the derivative of the second function multiplied by the first function. So f prime of x is, that's the 18x squared. We found that over here, right? And then the original function, g of x, was 7y to the fourth. That was from here. Then the derivative of g, that's here, 28y cubed. And then the original function f was 6x cubed. Multiplying this out, 18 times 7, 126 x squared y to the fourth, and then 28 times 6, 168 x cubed y cubed. So this is the derivative of that original function that we had. What I'm going to show you next is the proof of this product rule. And this is going to be lengthy, but we want to just make sure that if we're going to use a theorem or formula, that we can prove mathematically that it is true. So I'll go down here. So proof of the product rule. Let's start like we did in the example with a function capital F of x that is defined to be two functions that are multiplied together. Then when we want to take the derivative of that function, oops, just going back to our original definition of a derivative, we'll take the limit as h goes to 0 of capital F of x plus h minus f of x over h. Then what I'll do is I'll plug in this for my function. So I have f of x plus h multiplied by g of x plus h. That's for the first part here, for this part. And then we are going to subtract off f of x times g of x. That's for the second part here. And the whole thing gets divided by h. Now what we're going to do next is we're going to kind of do a little bit of a trick so that we can make this look the way we want to get a derivative and a function together. I'm going to do this by copying this. And moving it over here. But then what I'm going to do is I'm going to move this part over here. Okay. Move it over a tiny bit more. Because I'm going to write something in the middle here, so I want to have some room. So I'm just expanding this fraction. And I'm going to, in the center, I'm going to subtract off f of x plus h times g of x. And I'm also going to add the exact same thing. So what I've written there in orange nets out to 0, but I've added it so that I can use the first term to go with the, like I'm going to combine these two together, and then I'm going to combine these two together. So I kind of intentionally put those there so that it will get me to look the way that I want. So what we're going to do next, let's just focus on these two terms. They both have an f of x plus h that can be factored out. So I'm going to move the limit all the way onto the outside, just because we don't need to worry about it at the moment. Okay, let's do this. So I'm going to take f of x plus h. I'm factoring it out of those first two. And then I'm going to have left g of x plus h minus g of x. And I'm going to put the h down here. What I'm going to do is separate this into two different fractions. I'm going to have the first fraction be these two terms divided by h, and then the second fraction is going to be these two terms divided by h. And also in that same process, I'm factoring out this f of x plus h. So that's the first set. Let's look at the second set now. The second set is going to be, we're going to factor out from the second two terms g of x from both and bring that out to the front. And then we'll have this other fraction, f of x plus h minus f of x over h. Okay. Now what I'm going to do is, we talked about this a couple weeks ago, that when you have the limit of a function, you can change that into the limit of all of the functions sort of separate. So I'm going to distribute in a way the limit, I'm going to have it go to each of the individual functions that I have inside the large brackets. So I'll have the limit as h goes to 0 of f of x plus h. That's the first one. And then that'll be multiplied by the limit of this fraction. So that's still the first term. Then the limit of g of x, and that'll be multiplied by the limit of this other fraction. Zoom out a little so we can see the whole thing. Took the limit here, and oops, sorry, here, and I distribute it to all 4 of these items. And then let's look at each of them individually. This right here, if I plug h equals 0 in here, I'm just going to have f of x, right? And similarly here, this should be a plus. If I plug, there's no h involved, so this is just g of x. This is the formal definition of the derivative of g. And this is the formal definition of the derivative of x, or sorry, of f. So that's what we wanted to get for our formula that we're using for the product rule. So this is the proof of the product rule. The other theorem that we're looking at is the quotient rule, which is when you have 2 functions which are differentiable that are being divided. So I want to take the derivative of this quotient. This is a little bit more complicated, but if you look at the numerator, it looks the same as the product rule in a way. I'm taking the derivative of the first function, or in this case, the top function, and multiplying it by the denominator. Notice, though, that we subtract in this formula, and then we take the derivative of the bottom function and multiply it by the function in the numerator. And then the whole thing is divided by the denominator squared. The way that I learned this in high school was derivative of the top times the bottom. I actually learned it differently. Hang on, let me. I actually learned it's like when you say it over and over again after 1,000 years, you have it memorized. I learned the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. This is just written in the reverse order. They have the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So if you want to just come up with some way that you can to memorize this. Some people use high D low, low D high. You probably I've heard this, those of you that took calculus in high school. But let's do an example problem. Let's do an example problem. Let's let f of x, capital F of x, be equal to, I want to do y. Let's do y equals x squared plus x minus 2 over x cubed plus 6. We'll call this one f of x, and we'll call this one g of x. the derivative of the function in the numerator is 2x plus 1. And the derivative of the function in the denominator is 3x squared. So then when we want to find the derivative of the whole function, we're going to start with the derivative of the numerator, which is 2x plus 1. And then we're going to multiply that by the denominator, which is x cubed plus 6. Then we subtract the derivative of the denominator, so that's 3x squared, multiplied by the numerator, x squared plus x minus 2. And then that whole thing is over the function in the denominator squared. Multiplying that numerator out, let me make some more space here. We'll have 2x to the fourth plus 12x plus x cubed plus 6. And then I've got 3x to the fourth plus 3x cubed minus 6x squared. And then combining like terms, just to simplify. Let's see, I've got 2x to the fourth minus 3x to the fourth. So that's going to be a negative x to the fourth power. And then I've got an x cubed and a 3x cubed. That's a minus 3x cubed. So minus 2x cubed. We have, this is going to change to plus. And then we've got this guy plus 12x and plus 6. I think that's everything. Divided by x cubed plus 6, the quantity squared. In general, we don't want to multiply the denominator out because our goal is to find out where the function is equal to 0. That tells us where we've got horizontal tangents. And so we would eventually want to try to find the zeros of the numerator, right? So that we could figure out where the derivative is equal to 0. And then any of the zeros of the denominator tell us where the function is undefined, where we have potentially an asymptote. In this particular case, we don't have any asymptotes because the denominator is always positive. We've got that quantity squared, so any number that we plug into the denominator, the whole denominator is going to be positive. It's never going to equal 0. So in this particular case, we don't have to worry about any restrictions in the domain. But this lengthy, really big function expression that you see here, this is the derivative of that function. All right, so then what we'll do next is we'll do a proof similar to the product rule. We're going to do a proof of the quotient rule. All right, so I'm going to start again, like I did before, with just two generic functions. Let's let Let me scroll it. Here we go. F of x equal lowercase f of x divided by g of x. Then the derivative will be f of x plus h. Oops, I forgot my limit here. The limit as h approaches 0. Again, just starting with the basic definition that we were using for the first couple weeks of the semester. But this will be written in terms of that rational expression that we have there. So I'll do f of x plus h divided by g of x plus h minus f of x over g of x. And then that whole thing is divided by h. So this is a complex fraction because I have a fraction in the numerator. So what I'm going to do is clear those denominators by multiplying the whole thing by g of x plus h times g of x in both numerator and in denominator. So for the first fraction, these guys are going to cancel, and I'll just have f of x plus h times g of x. See, I'm talking about I'll have this left multiplied by this. And then for that second fraction, the g of x will cancel, and so I'll have this multiplied by this. So I'll write that here. That'll be minus f of x times g of x plus h. And then the whole thing, what has happened now is that the denominator has gotten more complicated because I've multiplied it by the two denominators that were in the numerator of the larger fraction. Okay, I think this is right. Okay. Now, kind of similar to what I did in the proof for the product rule, I'm going to do the same thing where I add in a term in the middle. I'm going to move this over. That equals to 0 so that it'll let me get the definitions that I want for the derivatives. So I'm going to add into the middle. Actually, this minus sign needs to go over here as well. So let's add it to the middle. We're going to put a minus f of x, g of x, and a plus f of x, g of x. So again, we've just added two things that net out to 0, but we're doing that intentionally so that we can group things in a way that get us to the definitions that we want. Now, I'm going to, similar to what I did before, I'm going to split this into two separate fractions, but actually, maybe I'll do this in two steps. The first thing that I'm going to do, I'll do this by copying this. Let's copy this whole thing. Bring it over here. Okay. First thing I'm going to do is I'm going to sort of separate the h's and I'm going to separate this whole denominator. And I'm going to do that by, I'm going to erase this for a minute. You'll see what I mean in a second. I'm going to put h here and h here. And then the whole thing is going to be over g of x plus h times g of x. What I did is I just took this and I wrote it differently. I put the h here under these and split this into two separate fractions. And then I kept the g of h plus x times the g of x down in a second denominator. When I'm just changing the way that we're looking at the division. When you have something, a fraction, like let's say that I have a over b divided by c, it's the same as a over b, why did I write a, times 1 over c. So b and c are still multiplied together. So what I'm saying is here in this fraction, they were multiplied together. I just rewrote it. I kind of went in this direction, that rather than having them multiplied together, I changed the way so that there was a fraction in the numerator and then part of it stayed down in the denominator. Okay, so now I'm going to tackle this part first, and I'm going to factor a g of x out of both. I'm going to out of both terms there in the numerator. I'm going to take the limit, and it's going to come way out to the front. So I'll have g of x factored out of both, and then what's left is f of x plus h minus f of x over h. Then looking at this second set of terms, I'm going to factor out an f of x. But I think I want to change this to be minus because in the quotient rule, we have a minus sign, right? I'm going to change this to be a minus. Just bear with me through for a second. I'm going to write g of x plus h minus g of x over h. I'll show you in just a second what I did. And then this whole thing is over the denominator. That denominator is just kind of hanging out there. Okay, what I did over here is I put a minus sign here and I put this term first. So that this whole part is that that second term. Because I have a minus sign here, this term needed to have a minus sign in front of it so that when I multiply these two together, it ended up being positive. There was a positive sign here. So I just kind of fudged it so that I need to get this negative sign in the middle because that's part of the formula that we have. All right, so I think we're ready now to take the limit and distribute it to all of the items that we have here, of which there are many. So I'll take the limit of g of x, and then that's multiplied by the limit of f of x plus h minus f of x over h. And then I'll subtract off the limit of f of x times the limit of g of x plus h minus g of x over h. And we're also going to distribute that limit down into the denominator. So it's going to every single function that we have. All right, so now let's look at each of these systematically. This first one, there's no h's involved, so when I take the limit, I'm just going to end up getting g of x. Similarly, This guy has no h's in it. So when I take the limit, I'm just going to get f of x. This is the definition of the derivative. So this is multiplied by the derivative of f. And similarly, this is the definition of the derivative. So this is multiplied by the derivative of g. Now looking at the denominator, if I plug 0 in to this function, I'm just going to get g, the limit of g of x. And so in the denominator, I'm getting g of x multiplied by g of x, which is that g of x squared. So this is the formula, and we've proved the quotient rule. In class, we will do a number of examples. It takes a lot of practice, and the more that you do practice of these problems, the more it becomes second nature. Thanks for watching, and I will see you in class.